All right, so yesterday we covered up to 4.4. And again, I understand those lessons were a little bit longer, right? Which is why we only got through 2 of them. So today, if we can get through 3, that's kind of the plan here. All right, because the only thing we have left in this unit 4 is 4.5 on experimental design, 4.6 on talking about publishing those reports, 4.7 here on applications, and then obviously 4.8 is kind of the wrap up here. All right, so my thought is that today we finish unit 4 here, and that gives us 2 days to kind of go over 5 as best we can. All right. So that's kind of my hope for us, is that we can go over all of that today. But if we only get through 2, then we get through 2 and just we kind of push some things back here. No stress, no worries. We're trying to, again, make this, of course, reasonable for us and for this class. All right, so if we get into a little bit of experimental design here, right? Again, just a reminder, yesterday we talked about how do we gather data, how do we make those inferences. Then we talked about some random variables, right? Like again, where you get a result randomly, how does that happen? Where does it come from? And now obviously if we talk about experimental design here, experiment being, again, the process of which you're collecting your data, right? So what are you trying to find? Who are you going to ask? What are you going to ask them? How are you going to ask them, etc.? All of that stuff, right? So again, we got to stop thinking about experiments just being in terms of science class here, right? You go out and you get public opinion on something, right? Maybe for a history project here, right? That's a type of experiment, right? You're going out, you're collecting some form of data, you're trying to make some kind of analysis here. All right, so experiments can be outside of just that science classroom setting. All right, so we talked though about these different types of data collection methods, right? So surveys, observational studies, and experiments. All right, and again, the surveys, I mean, all of them had pros and cons, right? But the observational studies, which were just looking at these subjects in their natural setting, right? So the one they talked about was observing people, do they put on their seatbelt or do they not put on their seatbelt, right? And there's a difference between the between observing them naturally and between the survey, right? Because in a survey, people are more inclined to be dishonest, and that was one of the things we talked about. Surveys have to assume that everyone is honest, but again, it's something like where you ask them, do you wear your seatbelt all the time? Right? It's something that people might be inclined to say yes, whereas in an observational study, you obviously know that they don't. Right? And then in an experiment, the slight difference between that is that your experiment here, you've got one group that's your testing group and one group that's your control, right? And the one example we talked about, that one was testing new drugs, right? Was testing new drugs. So again, there's 3 different types of ways that we really highlighted talking about data, and so now we'll talk about how those apply to experimental design. Ooh, there we go. Seems like my internet might be struggling again. Apologies, guys. And just like that, sorry guys, I don't know why my internet keeps cutting out on you. All right, sorry. So going back to our lesson here. Okay, so of course, now we got to talk about what is an experiment. All right, and in general, just talking about it, it is a method of collecting data in which you control the subjects in the study. right? So again, you can make this about people, you can make this about places, things, right? But in general, you're collecting some form of data, and you have to have control over the subjects or what you're doing, right? So then the two primary reasons for conducting an experiment is to establish a relationship of cause and effect between two variables, or to compare groups' responses to a particular treatment, right? So if this, then this, right? Those hypotheses type statements. That's what it's saying here for this first one. And then for the second one here is again, of course, trying to look at the difference between your experimental group and your control group, all right? So then when we're designing an experiment, our goal is obviously to find out about how our subjects respond, right? How our subjects respond to this response variable, okay? To this response variable. And again, of course, we know it as the treatment, right? Or we could say it as our independent variable, right? So again, if we go and look at this math class problem, okay, the school district wants to know whether a math teacher, whether teaching math in the morning instead of the afternoon will cause students' exam scores, will cause an increase in student exam scores. Okay, so this has the district has two schools here. Okay, Mr. Simpson teaches algebra in the morning, while Miss Bryant teaches algebra in the afternoon. Mr. Simpson's class has an average of 82, and Miss Bryant has an average of 60 or 76. Okay. So if Miss Bryant teaches her class in the morning instead of the afternoon, would her test scores rise? Okay. So that's a really, really good question here. All right, and that's what they're looking at. So this is the situation, and this is what we're trying to look at, right? And so obviously our response variable here, right? Our response variable is the testing scores, right? It is the testing scores. We're trying to see how the class tests. All right. Now, some other variables that could affect student achievement in these math classes are a lot, right? So like, what's the type of material? What kind of students do they have? Do they have longer class periods than other classes? Do they get a cheat sheet, right? How long do they have to study? All of these different types of variables can come into play. All right. And so there are a lot of different principles that we need to understand when we're designing an experiment, okay? And one of the first ones there is this thing called bias, all right? So bias means non-objective influence on an experiment, all right? All right, so it counts, bias is where, again, you're kind of influencing the experiment, right? You have a bias towards something, all right? So again, for here, the newscaster, she offers her opinion, all right? Well, her opinion is her personal beliefs, right? So that influences the way that the news is being reported. It's no longer objective, right? It's no longer objective. And there's biases in a lot of different cases here, right? And a bias can be just as simple as phrasing a question different ways, right? So one of the questions would be, or could be, we were talking about seatbelts, right? So maybe an unbiased question would be, do you wear your seatbelt every time you drive? Okay, that would be unbiased. But then maybe a biased way of saying this would be, well, of course, you wear your seatbelt every time you drive, right? There's two different ways of asking the same question, and one of them, obviously the second one, is going to influence the way that people answer that question. So again, that's an example of bias. All right. And while we can't completely eliminate all bias in an experiment, we can do a lot of things to reduce it. Okay, and basically there's four things here that we can do. We could do randomization, we can have a control, we can do blocking, and we can do replication. All right, so if we look at randomization here, all right, a lot of this is talking about getting rid of names, getting rid of labels, right, and assigning everything like a letter or a value, right, something where it's not easy to remember. And then you have a key somewhere else, right? So if you guys can all remember back to your biology class when you were growing plants, right? And you did a special treatment to it. Imagine if you had, I don't know, plants that you watered. Let's try to think about this. Sorry. Basically, right, you had plants that you watered every day, and you had plants that maybe you watered every other day, if that was your experiment, right? Regardless, though, you had to go in and measure the height of the plants every single day, right? And so in order to not be biased, instead of labeling it water plant 1, right, you could just label it plant A, right? And then you have your key later on to say, okay, plant A was supposed to get water every day, right? Again, randomize what you're doing, or randomize the order in which you do it. Okay. Obviously, having a control, right? This is the thing that doesn't get the treatment, right? So this is the thing that doesn't get the treatment. It's something to compare against or compare to. All right. Blocking. All right. So blocking is talking about separating experiments into groups that are similar. Okay. And again, what that does is it tries to eliminate a lot of outside factors, okay? Because then if there's something that happens, right, you can see it all together. So again, going back to our plant example, blocking might be, okay, if you're watering all these plants, right, in different times, you want to make sure though that they're all in groups near the windowsill, and not half of them in the windowsill, half of them in the back of the classroom, right? You want to make sure that they're all in little groups together, so that the outside factors aren't too terrible. All right, and then replication. Obviously, we need repeats, and we'll talk a little bit more about how do you know how many repeats you need. All right, but replication is key here. Okay, so how they looked at that math class problem was students are assigned random numbers. Okay, and that's to eliminate some potential bias here by looking at students differently, right? So students are assigned random numbers. The school system will study morning and afternoon classes, all right? So, and then perfect, right? Each teacher will be required to use the same test book, give the same exam, and teach for the same length of time, right? So some of those factors that we said would influence the test, right? We just try to control them there, all right? The experiment may only focus on one teacher's class. And then the replication, okay? The experiment's going to repeat it several times with different teachers or different times of the year. Okay, so taking a look closer at randomization, right? So again, to begin that process, you got to find a large number of subjects, or a large thing that you're going to study. And again, of course, you randomly assign them to either the treatment or the control group. And you can use random number generator, a random number table, right? That's kind of the two main things that we propose that you do for this randomization here, okay? And of course, you have to still have it written down here, right? You have to write it down here in order to make sure that you obviously can decipher that code later. All right, but it's not just, of course, it's not just giving them a random number, but again, having that random number means something. All right, so it can be used to tell you who's in the control and who's in the treatment group. All right. Of course, when we look at number generators here, all right, you shouldn't be able to predict the digits that come next. All right, and you can watch this video on your own here, but basically, of course, we talked about majority of them generate in these little blocks of 5, all right? And you can set whatever code you want to it, right? You can say, you know, we need half of the people to be controls, half of these to be treatment. If your number starts with an odd number, you're gonna be a treatment. And if your starts with an even, you're gonna be a control, right? Or whatever, but you can't tell, right? You can't tell your subjects. That's one of the only cases there, is that you can't tell your subjects, otherwise it defeats the whole purpose of randomization, right? So that the key that you decide on would stay between you and your team, whoever that is that's going to be running the tests on your subjects here, okay? You have to make the number generator work for you here. Okay. Then looking at this here, all right. There, I want you to go through this on your own here for the sake of time, but really look at obviously the importance of randomization here. All right. The importance of randomization. All right. And this one's talking about a taste test of carrots. Okay. It's talking about a taste test of carrots. So why would that be important? Okay. Why would that be important? All right. Then looking at obviously other randomization methods. Okay, you don't always have to use a random number generator class. There's a lot of different things. So for example here, choosing names from a hat is obviously random. Flipping a coin would be considered random. Cards from a deck would be random. Rolling a dice would be random. Okay, but things that aren't random are things like GPA is not random, right? Your GPA is not random. Okay, that would be breaking students apart by grades that they get in class. All right, teacher recommendations. Again, that would be merit-based. Okay, class vote is still not random, or test scores, right? These are things that people have influence over and could indicate some level of bias here, right? So that would be not random. All right. And then of course you noticed there's multiple times it says like a fair deck or a fair dice. All right. So again, of course, looking at things that are unfair. All right. Of course, there's ways to accidentally or intentionally change that process so it's no longer fair. All right. And of course, one of those could be, you know, drawing straws, or putting numbers in a hat in a certain order, right? Putting more numbers in a hat than other numbers, right? So again, it's all talking about you've got to make sure that it makes a fair selection process. All right, so taking a look at what might make some of these not fair, letting someone look in the hat before drawing, okay? Well, that would go with drawing lots, right? Lots meaning like something out of a hat, okay? Making one of the sections slightly larger than the other, okay? That would make spinning a spinner unfair. Having one of them weighted to one side, that would make rolling the dice unfair, okay? Having them marked in some way, that would be, that could work honestly for drawing straws or drawing cards, but what I think they're meaning for this one is drawing cards, because drawing straws is along the same way, but a lot of the times when you're drawing straws, it's like holding a bunch of pens in your hand. So it could have a secret signal for the participant about to choose, right? So again, there's a lot of things that make these potentially unfair, and hopefully they're kind of like obvious to you, but there's something that you do need to think about when you're designing your experiment. Okay, so bias can never be completely eliminated. All right, that's one of the main takeaways you have to understand. Bias can never be completely eliminated, unfortunately. We can do all these things like randomizations and control groups and design our experiments properly, but we can never, unfortunately, completely get rid of bias. All right, so then of course you guys can take a relook and summarize this, but there's a lot of similarities between the different types of data collection methods, but then of course there's a lot of differences here, and pros and cons to each of them. All right, and then of course the main one in this little unit here was the 4 types of primary principles here in order to try to eliminate that bias. So the randomization, control, blocking, and replication. All right, so those are 4 main things there. All right. So in an experiment, a subject or unit is exposed to an explanatory variable, and then the difference in the response variable are measured. Okay, so we're going to measure the difference in the response variable. Randomization reduces blank between treatment and control groups. okay? It reduces bias, all right? Again, it reduces bias, because if you don't know who's in the treatment and who's in the control, you can't try to modify or change it in any way. All right. Both experiments and blank involve collecting and analyzing data. All right. That would be surveys, right? Both experiments and surveys involve collecting and analyzing data. All right. And I'll let you guys go through this, check your understanding here. Again, the key is try to read it and understand what they're asking you to do here, right? With these problems in this unit here, the biggest point is asking or figuring out what question they are asking you, okay? So it's try to figure out what question they're asking you. All right, that's my key there. All right, moving away from randomization here to now looking at control and lurking variables. All right, so of course, it's a good practice that we should get our treatment group and our control group. All right, and that of course is part of this concept of control. Okay, and control helps us make sure that our explanatory variable is what's really causing an observed change. All right, so what this is when they mean explanatory variable, they mean our independent variable, or the variable that is explained as the reason. Okay, so don't let this confuse you here. Explanatory variable is the variable that is explained as the reason, otherwise known as our independent variable. Okay, a variable that is not noticed is called a lurking variable. Okay, it's called a lurking variable. All right, and it may or may not have an effect on the outcome of an experiment. All right, so earlier we were talking about our plant growth from biology class, right? So one of the lurking variables in that might have been temperature in the room, right? You might have been trying to study water, right, as your explanatory variable, but temperature might have had an effect as well. Okay, and we can say variables are confounded, which is unknown as to causing any effect. All right, so if we have a lot of variables and we don't know which one's causing it, we can call it confounded, right? We can call it confounded. So again, if we look at this math problem here, we've got lurking variables, which are things that may have an effect. All right, so difficulty of the test might have an effect on the outcome. The time the class is taken might have an effect. Amount of homework given, distractions in the classroom, effectiveness of the teacher, math ability of the student. I don't believe the school district. Oh, but it is apparently. And so is the subject being taught. Okay, so, oh, here we go. I was like, what the heck? That doesn't make sense. All right, apologies. All right, so things that aren't lurking variables is the time the class is taken, the school district, and the subject being taught. All right, and the reason that these are not lurking variables is because when we go back to our math problem, remember, we're looking at two teachers teaching math class. They're both teaching the same math class. So it can't be the subject being taught because both teachers are teaching the same subject. All right, it can't be the school district because both of those teachers are in the same school district. However, it might be the effectiveness of the individual teacher, right? Teacher A might be really great and teacher B might be a little bit not as great, right? And the last one is the time the class is taken, right? Because if you remember, we took a step on the last couple of slides here to eliminate that by testing both in the afternoon and in the morning, right? So flipping and looking at both of those times here, all right? So these are three that are not considered lurking variables because we've already taken them into consideration and really done a job at controlling them. Okay, now if we look at blocking here, all right, if we look at blocking, what blocking is going to do is it's going to help us chunk together students in order to avoid making another lurking variable, right? Making another lurking variable. All right, so for example, if the students are randomly placed into each class, the lurking variables of students' abilities are dealt with, okay? But it doesn't deal with teacher effectiveness, okay? It doesn't deal with teacher effectiveness. So one way to deal with this is through a special control technique, obviously called blocking. All right, so if we only are studying Mr. Simpson's classes, all right, this eliminates the problem. Then we do the exact same thing with Miss Brandt. Okay, Miss Brandt. All right, and what they're saying is we block all of Mr. Simpson's classes together. So that way we're not trying to compare Mr. Simpson to Mrs. Brandt. Okay, we're just comparing AM to PM, which again was the ultimate question. Does taking the class at different times affect your scores? All right, same thing here with Miss Brandt. Again, it's not comparing Brandt to Simpson, it's comparing her AM to her PM class. Okay, so this is a good way of doing this here. All right. And in a lot of these here, okay, it's saying our control variables are referred to as treatments in the experiment. Okay. However, in this experiment here, we're doing a treatment in the morning and in the afternoon. Okay. And what it's saying is one of these is one treatment and one of these is the other, right? Because the treatment is the time that they're taking the test. All right, but again, blocking is another way of helping us. Blocking is another way where we can control another variable. And when we did that one for this specific example, it was limiting that we have to compare teacher to teacher, and now we can just look at the times. Okay. Then we have two other lurking variables that can cause, we have lurking variables that can cause two other special effects here. All right, the first one is called the Hawthorne effect. All right, and then the second one is called the placebo effect. All right, and hopefully you've at least heard of maybe the placebo effect here. All right, in the Hawthorne effect, if we read this here, subjects change their behavior because they know they are in an experiment. All right, so for example, if students know they're in an experiment studying the time of math class, they might study harder or slack off, right? Or in the example of seatbelts, okay, because they know they're being watched to see if they put their seatbelt on, people might be more inclined to wear their seatbelt. Right, so this is called the Hawthorne effect, where again, they change because they know they're in an experiment. Now, a placebo effect is where subjects respond physical or mentally to a treatment, whether or not it has the actual effect, okay? So a good example of this would be is if we were studying a new drug, right? And what they do is they give everybody, okay, whether or not you actually get the drug, everybody gets a pill. And half of the people get the treatment pill, and half of the people get what's called a sugar pill. All right? And they want to see what effects people are reporting, because if people with the sugar pill automatically report that they feel better or they feel all of these, positive symptoms here, then it could just be this placebo because they believe that they got a treatment. All right, they believe that they got a treatment. Okay, and so again, here's two more examples here. So if students see in the morning class do better in the afternoon, okay, the Hawthorne effect, the students in the morning class might study more because they know they're an experiment, and the additional time studying might result in higher scores. Okay. For here, to see if a new soda with extra caffeine affects one's energy level. Okay, so half of the people are going to drink the new soda with more caffeine. Half of them are going to drink non-caffeinated soda. All right, and in a placebo effect, all subjects believe they have more energy because they were aware that the new soda had more caffeine. All right, so basically half of those people, at least half, right, reported out false information unknowingly. They felt better because they knew that the soda that they were given should have more caffeine, right? It's kind of a crazy thing to think about it if you take a second here. And then if this kind of stuff is interesting to you, I know there's definitely stuff about that in psychology here. All right. And again, quickly, placebo, right? Again, it's talking about giving a fake thing so that everybody thinks that they have that treatment. And of course, placebos are not. Okay. And again, in order for a placebo to work, subjects cannot know if they are in the treatment or the control group. All right. So this is what we call a blind experiment, and it's a method of reducing bias. Okay. So again, if you want to try out a new medicine, all right, you just get everybody in the same group, or you can even chunk them, but you don't tell them if they're going to be a control or a testing variable. Okay, you just give them the pill, whether it's the treatment or the placebo, and you measure the outcome as received. Okay, so again, it helps prevent some of those lurking variables. All right, but bias can also come from the experimenter. All right, and so that's why it's important also to keep an experimenter blind who might be receiving the treatment. All right, so and again, an example of that is when you're asking questions, if you know that somebody is a placebo, you might ask them differently. So a way of doing or getting around that is what we call a double-blind experiment. All right, so that would be where the tester doesn't know who is who, and neither does the actual tester or the person, sorry. There is a key somewhere that says, participant A had a placebo, right? And you can decipher all of that later, but when you're collecting the data, everybody needs to be effectively, quote, blind for this to work here. So again, in a blind study, the subjects won't know that the blue pill is a placebo. In a double-blind study, neither will the researcher, right? Neither would the researcher. Okay. And then obviously replication, okay, replication. Once you've got a method down, you like the method, you think it gives you some good results, you have to repeat the process, okay? And the reason you repeat that is to try to, of course, minimize bias. And it can be a lot of different biases, right? But like, if the students studied really hard that one time, well, if you repeat it, are they going to continue to study, or was that just a one-time fluke, right? So a lot of things, there's a lot of benefits to replication, all right? And one of them is, of course, replication means doing the experiment with many groups of subjects with many different types of tests if possible, all right? And it could also be more than one researcher doing the experiment, so it reduces bias here. All right, and so then we look at this question here. What conclusions can be drawn if the results of a replicated experiment are not similar? Okay, what are 3 things that we can decide here? All right, well, first, the experiment might not have been replicated properly. That's always a possibility, right? Maybe you did something the first time that you didn't share the second time. All right, maybe the experiment was designed poorly, right? Maybe just overall it wasn't a great designed experiment. This third one here, though, is not true. The experiment proves a hypothesis. Not if you can't repeat the results, right? You have to be able to repeat the results. All right, and then finally, the experiment may have been poorly executed, right? That's another one, okay? So either you didn't have it executed well, it wasn't designed well from the start, or the person replicating it didn't know all of the ins and outs, and it might not have been able to be replicated exactly the way that it should have. Okay. So then, of course, when we confirm all this information, reducing bias by making sure that the subjects do not know if they're in the treatment or the control group is called blindness, right? It's called blindness. And of course, we can help with this blindness by using a placebo, right? We can use a placebo. Okay. And matching up our experimental designs with our term words here. So physical or mental response to a treatment, whether or not the actual treatment is being tested, that is called the placebo effect. Apologies, placebo effect. All right, not just placebo. An inactive treatment given to a group, that would be your placebo, right? So not a full treatment, right? That sugar pill, the control. A change in subject's behavior because they know they're part of an experiment. That's your Hawthorne effect, all right? An experimental design where neither the experimenter nor the subjects know who's in the treatment group, that would be a double-blind experiment, all right? Repeating an experiment on different subjects under different conditions, that would be replication, all right? Using a treatment group and a control group, that's part of the control. Separating subjects into groups that are as similar as possible, that would be blocking. And then finally, a design where the subjects don't know where they are is called blindness. All right. So taking, again, of course, you can do that on your own and take a look and understand that. All right. And same thing here. All right. I want to leave these up to you. Make sure you do them because, again, it's talking about reading this entire thing and figuring out which of the principles were involved here. All right, figuring out which of the principles were involved here. Okay, of course, please go through and do those, guys. All right, and now getting to our study sheet, we did a lot of recap throughout, so I'll fly through this here. But again, the main purpose of experiments is to establish a relationship of cause and effect between two variables and to compare two groups' responses to a similar treatment. All right, and we have a lot of principles here, right? Randomization, control, blocking, and replication, and all of these principles are used to try to eliminate bias, right? We don't want to try to control the outcome of our experiment. We want the outcome to be what it's naturally going to be. So we have those 4 ways of looking at it. All right, and first we talked about randomization, right? So giving subjects numbers, maybe getting random digits from a generator or from a table, right? Doing a lot of different things here. Okay, and here was a really good example that you can go through of actually taking a random number generator and pulling out digits for each of the subjects here. Okay. Then, of course, we talked about the difference between the placebo and the Hawthorne effect. We talked about blind versus double blind. And, of course, the ultimate goal is to always reduce our bias here. All right. And, of course, this one here is talking about a specific example. So if there's 100 subjects in the experiment, 50 are men, 50 are women, and then you want to test how well ginger pills relieve motion sickness. Okay, so it's going to ask you to answer some scenarios here. All right, so to answer some scenarios, and the one that I want to focus on is describe a block design that will control differences in the way men and women respond to the ginger pills. Okay, so what they're asking is to chunk people together, right? Chunk people together that highlights differences between men and women responses, all right? Because what it tells you up here is that you have 50 men and 50 women total in the experiment. It doesn't tell you who's getting what. So this question here is asking you to decide and chunk them together, right? Block them together. So really what this question is asking you to figure out is that of your 50 men, 25 of them should get the ginger pill and 25 of them should get a placebo. Same thing should happen with the women, right? That way you don't give all the testing variables to the men and the women get the placebos, because there might be an unintended or a lurking variable that comes as a response to the difference between men and women. Okay, so again, things along those lines, right? You're trying to make this as fair and as unbiased as possible when you collect your data. All right, so try to keep that in your mind there. All right, for your checkup, of course, it's going to be a lot of practice problems here. It's going to be a lot of practice problems, and of course, using the following printable, right? It's presented below, so you guys can use this to answer the practice problem questions here. All right, and then it repeats, of course, for 7 through 10. All right. So again, taking a minute, at least do one of those little chunks there before you get to your quizzes for this unit. You've got 2 of them. Okay, so you've got one on sampling and your simulation, and then you've got one on experimental design. So you've got 2 quizzes for this unit here. All right, and then we'll move on to evaluating published reports, okay? This one I super love because it's talking about things that other people have reported out. So looking at them with kind of a critical eye here. All right, so for example, it says a recent survey by the Independent Poll Research just announced that 75% plus or minus 3% of Americans like the idea of a 3-day weekend. Okay, so immediately when you read that, you might have some questions like, who's the 25% that don't like the idea, right? Or I always ask, well, who the heck did they ask for this survey? How did they get that number? All right, some of the other ones that you might now ask here is was the sample selected that created some bias, right? Do they have some bias? Is this even a real organization? All right, and then finally, that last thing that we may or may not have talked about is this plus or minus 3% here, okay? So of course, we can look at that here. All right. So looking at surveys here, or just data collection in general, there's always what we call this margin for error. All right. And basically what it's saying is there's always a chance that something went wrong. Right. And we talked a lot about this in chemistry class. So sophomores, you'll learn more about it later on, but my juniors learned a lot about this error, right? So there's error in everything, right? When you're reading if you're reading a graduated cylinder or a beaker, right? There's going to be some error in that, right? There's even error in things like your digital thermometer, right? There's an error in that, and we can always look at that later, but there's, again, it's called this margin for error. All right, it's saying I'm accurate within a certain degree of error, right? How we report that is a plus or minus sign, right? So it's saying I know between 75 plus 3% and 75 minus 3%, right? So I am confident. I'm very confident between 78 and 72% of Americans like this idea, all right? So again, 72 to 78% of the people like this idea. All right, and if you add in your original answer plus or minus your margin for error, this is what's called our confidence interval. All right, so again, like I just said, it's like saying I am 95% confident, right, that they're gonna fall somewhere between 72 and 78. All right, so again, it's talking about how confident you are that your answers are gonna fall between those values. Okay, so it could be also called a confidence variable. All right, and of course, another thing to highlight here is that the company's not claiming that 75% is the real value. Okay, they can't know how all Americans feel, but they can base their claim on the sample that they asked, right? So they can always say, right, out of the people that we asked, 75% of them said blank, right? And of course, the margin of error is to measure how much we trust those claims, okay? So if we go forward here, all right, when we talked about the confidence, right, when we talked about our confidence interval, so you might ask, why 95%, right? Why did we say 95%? All right, and a 95% confidence level is arbitrary, which means it's like a fake number almost. All right, it's used to indicate the reliability of an estimate. All right, and it's what most people use. They like to say we're 95% confident, right? Because it still leaves that small small room for error here, okay? And again, the reason that 95 was picked is because of this empirical rule, all right? And we talked a lot about it, but looking back to yesterday's discussion here, right, we talked about our 68, 95, 99.7 rule, and that was talking about our 1 standard deviation, 2 standard deviation, 3 standard deviations away from our mean. All right, and so our empirical rule here, if we're 2 standard deviations away, that's 95% of our data, right? So 95% of the data will be within 2 standard deviations of our mean, right? So that's how we get this value of 95%. Okay, that's how we get this value of 95%. All right, however, a lot of people have to do more than 95%, right? Like, will this drug work? Will this building withstand an earthquake? Right? Normally with things like that, we have to aim for higher than 95%. Right? We want to try to limit the error as much as possible when it deals with, of course, public health and public safety, right? Okay, so then looking at the question of sample size, right? So looking at the question of the size of our sample. Okay, it obviously impacts the confidence in our claim here. Right, so again, if we want to estimate the average height of a student, is it better to sample 1 or 2 students? Okay, well, 1, if we pick 1 student at random, okay, is she likely, or is he or she likely to be the average height of the entire school, right? Can we be 95% confident that this person will have the average student height? Or did you pick an outlier, like a center on the basketball team? Okay, so if we pick 2 students though, okay, even if 1 person is this outlier, right, the likelihood that the second person is a outlier as well is very, very low. So that second person is probably closer to our population average, okay? And so as we pick more people, we become more and more confident that we are getting closer to our average number or our average height here. Okay. And I would probably say value D here. All right, so it says, which do you think would be the best for creating a representation of the population average? The answer would be 4 here, because more data can sometimes give misleading results. However, when we're doing averages, okay, when we're talking about averages here, more is usually better here. Okay, so even though despite this one really tall person, right, the more data that we collect, the more likely we're going to be accurate here, right? The more likely we're going to be accurate. All right, and then of course, obviously we know that many samples is better than just the 2 people. All right, because of course, we're trying to connect our confidence level, confidence interval, and our sample size. So the more people we get in our sample, the more likely we're going to be within that 2 standard deviations, right? So we're going to be within our confidence interval, and we're going to just increase the amount of confidence that we have in our results here. Okay, and when we decrease the interval of which we're confident, right, we are also decreasing our margin of error. All right, so instead of, I guess I should say this, instead of increasing our confidence level, we can instead decrease the interval over which we are confident, right, which means we decrease the margin of error. All right, so again, instead of looking at from 0 to 100, saying, you know, our students are on average between 0 and 100 inches tall, okay? That's a really, really large confidence region, right? So instead of looking at this entire interval, we can shrink it and say, okay, we know our students are between 55 and 75, right? So we're shrinking that confidence level, which means we are gonna have less likely a chance for error, right? So we bring our error down here. Okay, and that's basically what this is saying here. All right. And again, margin for error is plus or minus the distance from our average value here. All right. So again, the closer we get to an actual average and the tighter our distribution of data, the less of a chance we have for error. Okay. So then looking at our distribution of our means, right? So we talked a lot about this where, of course, our sample means was with this X bar here, all right? And we talked about estimating based on our probability, okay? And looking at, of course, a normal distribution. And we talked about how a normal distribution has that bell shape. I was hoping it would show you a picture of it, but it has that kind of bell shape. All right, it is centered at the mean, and it has a standard deviation of our sigma over square root of n. All right, sigma over square root of n. All right, and again, the empirical rule, that what this is saying is a lot, I know, but basically it's saying one standard deviation away from our mean. Okay, so one standard deviation away from our mean has 68% of the data. 2 standard deviations away from our mean has 95% of our data, and 3 standard deviations away from our mean has 99.7% of our data. Okay, it has 97% of our data. All right, so then here, the soda study example, okay, so it's looking at how many sodas are consumed by teenagers. They know that a standard deviation of about 20 sodas per month, okay? And I guess I should say the sample mean, right, the average amount is 55 sodas, plus or minus the standard deviation of 20. So people could go up to as much as 75 and as low as 35 sodas, right? That's the standard deviation there. Okay, and so when they did the standard deviation of the distribution of sample means, right, big words, all right, you can calculate that as 20 over square root of 100 because it's the standard deviation of sodas over the square root of the people sampled, okay? So 2, right? So 2, all right? And so what this is saying here is our sample mean of 55 sodas is within 2 sodas or 1 standard deviation based on our calculation, all right, of our population mean 68% of the time, all right, 68% of the time. All right, and again, 68% because we're talking about 1 standard deviation. All right, 1 standard deviation. And because of this 2 soda confidence, right, we now create our confidence interval being plus or minus 2 sodas from 55. Okay, so we go down to 53, up to 57. All right, same thing with our 2 standard deviation and our 3 standard deviation. So if I look at 3 standard deviations here, all right, this would obviously be a 3 out front. Okay, so it would end up being 3 times 2, which gives us our 6 soda interval. Okay, and again, we are 95 or 99.7% of the time, this is what it's going to be because again, it's 3 standard deviations, right? So our standard rule there, okay? And then our confidence interval, of course, goes 55 plus 6 and 55 minus 6. Okay, so that would be our confidence interval there. All right, so looking at an energy drink here, okay? I will let you guys go through this one on your own here since it doesn't look like you have to click and drag anything. All right, so this is another good example for you to walk through here. All right, And then of course, practice calculating those confidence intervals. All right. And I know that these symbols are a little bit potentially confusing. All right. But all you have to do is match them up to the equations that you were given on a couple slides ago. I believe like 3 slides ago. Okay. So again, N is talking about your sample size. All right. X bar is talking about your mean, right, or your average value. This CL is your confidence level, right? So this is going to tell you, are you going to be 1 or 2 standard deviation, 1, 2, or 3, sorry, 1, 2, or 3 standard deviations away, right? 68 is 1, 95 is 2, 99.7 is 3. All right, so that's talking about what level of standard deviation are you away. And then, of course, this sigma here is talking about your standard deviation. All right, so once you do that, though, okay, you should be able to calculate whatever your value is. You should be able to calculate whatever your value is. All right, and then what you're going to notice here is, so this first one matches up here. All right, and you can do the calculations, right, and what this is going to tell you is that this is a confidence interval, right? So since we're only going to we're only 1 sigma away, right? We're only 1 sigma away because it's 68% here. When I do my calculation based on 22 divided by the square root of 121, all right, this gets me a value of 2, right? This gets me a value of plus or minus 2. So when it's asking you for your interval, it's asking you for, okay, take your average value minus 2 and plus 2, right? So for 42, minus 2 brings me down to 40, up 2 brings me up to 44, okay? So you'd have to do that guy, all right, a couple times here, all right? And you can't just always look at it and know what it is. You actually have to make sure you can do some of these calculations, so double check that for me when you're going. Okay, then here we have unknown population variance, okay? So we've talked a lot about confidence intervals, sample mean, sample size, right? Our population standard deviation, but what happens if we have a really large sample set here, right? It's talking about n greater than 30, okay? So n greater than 30, all right? And what this does here is it brings our sample standard deviation, right, really, really close to our population standard deviation. And the reason that could be is because we get a really large sample set here, okay? And again, that's the key. You can only do this when n is really, really large, okay? So, of course, once you do that a couple times, you can practice a couple more. And if, of course, it's dealing with really, really large numbers. Okay. Then looking at confidence intervals with sample standard deviations here. All right. If you conduct this survey or your experiment, right, then you can have these confidence intervals and your confidence level, and we can know that it's accurate, right? And you can know that it's accurate. So looking here at this study, okay, it's sometimes easy to spot problems related to bias or design flaws, right? So for example here, if we look at Bob's Burgers, it's clearly the most preferred brand of hamburgers among fast food restaurants. In a survey of more than 5,000 people, 90% of respondents claimed to prefer a hamburger from Bob's over a hamburger from any other fast food chains. Respondents were chosen from individuals who were visiting Bob's Burger fan club website and volunteered to take the survey. Okay? Hopefully you notice a giant red flag there. Okay? They only asked people who visited the Bob's Burger fan website, okay? They didn't ask everybody. They asked people who have been to Bob's Burgers and who clearly have subscribed to something saying that they liked it, right? So that would be pretty problematic here. Okay, and so then we have to go back and look at the design of the experiment. Okay, and that would go back to what we just talked about. They'd have to look back at the design of the experiment. All right, and this is one thing we call is selection bias, right? They were biased by selecting people particular to giving them a result that they wanted, right? So you can look at this more here. All right, but again, we learned about how to try to make our sample set a little bit more free of bias, but this is a very obvious one. Okay, so as a result there, we can't trust the results that they generated. Okay, or you report them, but you have to say out of the people that have eaten Bob's, right? Like there has to be some kind of disclaimer there, otherwise you're putting out false information. Okay, so then looking at this one here. Okay, of course I'm going to let you guys do this one and see if you trust this experiment and if it is flawed in any way and why. Okay, another one we talked about here, we talked about making an accurate amount of samples here, and again, one of the issues that happens with a lot of surveys or when we're trying to make statistics for things is you have too small of a sample size, or they'll say a poor sample size. All right, so for example, if you ask too few people, right? So if this town has 50,000 people and you've only asked 3 people their opinion, right? That doesn't give a whole lot of confidence behind what you were saying here. All right, so that really could shift the way that your data is perceived. All right, and so you've got to think about getting larger samples and making sure that you're still trying to limit that bias as much as possible. Okay, so here's another example that I'll let you read and look at it, but it's about basically gun control, right? And it says over 65% of survey respondents answered yes. Okay, and of course the question you need to then read through here is well, who asked the people? Where did they get these people from? Right, all of that stuff. Okay, and what we're going to find here is that it looked like originally that the experiment seemed to be done correctly. Okay, the researchers used a large sample size, they asked a simple question, they reported the results. However, the way that they looked at their results is problematic here. Okay, because gun control is not the same thing as banning gun ownership. All right, so the way that they asked the question and the way they interpreted it is 2 different things. Okay, is 2 different things. So you might have the perfectly well-designed experiment, but if it doesn't ask the question that you really want answered, or it doesn't ask the question in the way that's obvious to the respondents, you can still have a poorly designed experiment here. Okay. So then there's a difference here between correlation and causation. All right, correlation and causation. All right, with causation, it's a cause and effect, right? So one thing caused the other thing. All right, one thing caused the other thing. Okay, if things are correlated, all right, it's talking about things that are linked in some way, but are not necessarily the cause of the other. All right, so the example they gave here was the snowfall melting all at once and is causing floods. All right, increased skiing in the winter is not the cause of floods. However, the 2 events are correlated. All right, the 2 events are correlated. Okay. So again, there's a difference between correlation and causation. All right, if 2 things follow a pattern, they can be correlated. All right, but it does not mean that they have causation or one causes the other. All right, so this is something that you need to take into consideration. Does one thing cause the other, Or do they both happen, or is there a relationship between why they both might or might not happen? Okay. And unfortunately, right, they titled it perfectly. There's no easy answer a lot of the times when you look at causation or correlation. Okay, sometimes it can be kind of dicey here, and especially on that last page, it was talking about SAT performance. Okay, so performance on a standardized test there. All right, and so sometimes it can be really, really difficult to pull out if it's a causation or correlation. All right. So in other words, there's many conclusions that you can come to. Many times there is no simple, straightforward answer to the question posed at the beginning of a study. All right. And in general, though, that's the nature of a good research question. It leads to additional interesting questions, right? I'd love to say it in my science classes. If you ask a question that you can go and Google the results, that's not a really good experimental design, right? You want something that asks multiple questions, okay? And then, of course, looking at the confidence, right? So how confident are you? Are you 1 sigma, 2 sigma, right? All of that kind of stuff. And again, of course, that leads up to accuracy of your conclusions, okay? If you've done your experiment well, if you collected your data, if you were unbiased, if you did all of this stuff here, right, and you tried to analyze the data and you found this stuff here, all right, of course, the next things come to was our confidence level and our confidence interval, right? So we can do that as a way of talking about our accuracy of our conclusion, right? And our accuracy of our conclusion. And again, one way that we can improve this accuracy or our confidence is to increase our sample size, right? If we ask more people how they feel, we could get a more accurate estimate of how people truly feel about something, right? It could give us a more accurate conclusion. All right. And then, of course, another thing to look at and to try to promote is this thing called honesty. I know it's a novel concept sometimes, but we always want to make sure that we're reporting with accurate information and being as honest as possible, right? Of course, that is kind of in the code of ethics for researchers, right? And again, you'll talk about this more in your science classes here. But pretty much when you're publishing these reports here, everybody tries to go by a code of kind of ethics and making sure that they're promoting this honest information, right? So promoting the dissemination of honest information here. Of course, that's going to be a big one. All right. And then if you're gathering information from somewhere, right? If you're doing a little bit of maybe background research or you're finding statistics online, okay, you need to ask yourself, where is this source coming from? And I'm assured you've talked about this in English class, was citing your sources, but of course it is important to know who did whatever you're looking for, right? We talked about, or I'm sure you've talked about a lot of like using a .edu instead of using a .com, right? So, or using a .org instead of a .com and all of that stuff. All right, same thing with statistics here. With statistics, if a company, usually it'll have to tell you what company performed the experiment in order to get the statistics, right? So if you were asked to evaluate that source, you could look up information on that company and see some basic information about them, right? Where are they located? Who did they sample size, right? Have they had any issues in the past? All of that kind of stuff. All right. So of course then here there's a lot of things we talked about with evaluating published reports, all right, and mainly looking at what are the things that researchers get wrong and how confident do we want to be and how do we increase that confidence, right? Again, more practice problems, please take a look at them. Same thing with the check your understanding. I don't want to take those practice away from you. Okay. Looking at here our study sheet here. All right, a poor study design due to selection bias. There's a lot of examples that you can have here. All right. But the 4 characteristics of study design are that are important is, of course, looking at how was the study conducted, who conducted the study, what questions were asked, and where was the study conducted. And these 4 questions are going to be key when you are evaluating any piece of information that you could possibly be given. How was it done? Who did it? What did they ask? And where was it done? Okay. And if a sample represents those who feel strongly about an issue, we cannot trust the results. Okay, we cannot trust their results. And the reason that is because they're inputting their bias, right? They're inputting their bias. All right. And some of the things we talked about was, of course, poor study design due to small sample size, right? So what happens and why does that happen? Okay. And if they have a small sample size, they are less likely to reflect the true feelings. All right. And then we talked about poor analysis in a study. Okay. Right. You don't ask the question the same way you interpret it, right? Or you do some poor errors in your calculations here, not looking at it correctly. All right. Then we talked about misunderstanding between correlation and causation, right? So some things can be correlated, right? They can have a relationship between them, but it might not be a cause and effect relationship, right? It might not be a cause and effect relationship. All right, now we talked about, of course, confidence intervals and confidence levels. And of course, that goes back to looking at that normal distribution, right? That bell curve, and having the mean and our plus or minus our 1, 2, and 3 standard deviations away. Okay. And then, of course, talking about honesty, talking about ethics, and trying to ask for obviously honest answers there. Okay. And then looking at the checkup, of course, it's going to be a lot of practice problems here, identifying issues, right? Identifying issues that will either help or hurt a current situation here, and then being able to calculate some of the confidence intervals. Okay, being able to calculate some of the confidence intervals. Again, paying close attention to what percentage confidence do you need, because that's going to tell you, again, are you 1, 2, or 3 sigmas away from your mean? Okay, so again, paying really close attention to what % confidence, that's going to tell you your sigma value there. Okay, and so it looks like we're going to stop here. So we only got through 2 lessons, of course. So we've got 4.6 and 4.5. So we've got 2 quizzes here, 1 quiz here. All right. And tomorrow, of course, we'll finish up lesson 4 and move on to lesson 5 here. Okay. So if you want a prequel again, of course, as to what we're doing tomorrow, we're going to finish lesson 4.7. We'll quickly review 4.8, which wraps this unit up, and then we'll at least touch on 5.1. Okay, so feel free to work ahead today if you want. You can go and look at that stuff on your own, or at least finish what we covered in class today. Okay, other than that, guys, if you've got any questions, reach out, but I'll let us out about 13 minutes early so you guys can get started on that there. All right, have a good day, and I'll see you guys tomorrow.